Okay, so this is the first lecture for VLSI design. We'll start with what VLSI means. VLSI is basically a short form for very large scale integration. It is a manufacturing process wherein we are incorporating thousands of transistors or electronic components on a single chip. So what is important to note over here is this term large. What does this term large mean? What does it indicate? The large term over here, it does not mean that the size of the device or the size of the chip is large, but it means that we are incorporating a large number of transistors on a single IC. Now earlier what we used to have is what we called as a discrete circuit. Discrete circuit is a circuit wherein the components, the electrical components like the transistors, the resistors or the capacitors, they were joined with wires. The main concern with these circuits is that their area is very large and the speed is very less. So now let's just take a simple example of a cell phone or a laptop. When we want to buy a new cell phone or a new laptop, there are different specifications that we have in our mind. And one of these specifications is area or the weight of the device. We want our cell phones to be slim. We want them to be light in weight. We want the area to be small. We want them to be compact. Okay, and also another very important specification is the speed. We want our speed to be very good. We want our device to have a very high speed. So these devices, what they had was a very large area and the speed was comparatively less as compared to what we can achieve with VLSI design. Okay, now the main advantage that VLSI offers us is that first there is only a single chip that we use, a single integrated chip, and then the speed is increased and the area is very small, and because the area is small, our device is compact and a good speed is always required. Okay, now the number of these transistors on a chip, they help us in classifying the families of these ICs. What we have, we have three categories over here. One is MSI, second one is LSI, and the third one is VLSI. Okay, MSI is medium scale integration, LSI large scale integration, and then our course, that is VLSI, that is very large scale integration. Okay, so the medium scale integration is wherein we have approximately 100 transistors per IC. Okay, so for example, if I have an IC with area A and I incorporate or integrate 100 transistors on that IC, in that case my technology will be called as medium scale integration. If on the same chip I integrate 1000 transistors, then it will become large scale integration. And if I am able to integrate millions of transistors, then it will become very large. That means a larger number of electronic components like transistors on a particular chip. So VLSI is wherein we have millions of transistors on a single chip. Okay, now we will come to a law which is called as Moore's law. Moore's law is what it states is that after every 18 months the number of transistors on an IC, they will double. Okay, they will double in number. Now this Moore's law, it has been there for a very, very long time and it will be there for a very long time in future. However, not in its absolute terms. What I mean to say is that earlier what we would say is that after every 18 months the number of transistors, they would double. Now because the technology has it has now it is starting the number of transistors that we were able to integrate on a single chip, they have now started we have now started reaching a limit wherein we cannot say that after every 18 months they will double. We can say that after every 18 months there will be an increase in the number of transistors, or in other words we can say that not only it won't take only 18 months, but maybe a larger amount of time for the number of transistors to double. So in the world of today, although Moore's law is valid, but we cannot say that it is valid in its absolute terms. It has started showing a slowdown, and maybe it will be it will hold for some time to come, but whether in its absolute but definitely not in its absolute terms. Okay, and whether it will be 18 months or more, or whether it will be double or less, that is to be seen. Okay, now in VLSI design, the device of choice is MOSFET. MOSFET is the device that we usually use for our VLSI design. Okay, and MOSFET, as you must be knowing, is metal oxide semiconductor field effect transistor. This is something that you must have read earlier. Now there are a few advantages of MOSFETs that make them the device of choice. The first one is that they have a relatively small area. There is less noise because it is a unipolar device. There are only majority carriers, there are no minority carriers in this device, and as such the noise it reduces. Then they show less dependence on temperature. That is, with temperature, with an increase in temperature, their parameters, they do change, but they do not change to a greater extent like we have in case of BJTs. Then the manufacturing process of MOSFETs, it is simple as compared to your BJTs. Okay, so MOSFET is as we say, it is a voltage control device, and it is unipolar voltage controlled because the application of gate source voltage and drain source voltage, it basically affects the operation of the MOSFET. Okay, now these MOSFETs, they are of two types. One is enhancement MOSFET and the second one is depletion MOSFET. Enhancement MOSFET is wherein the channel, it is enhanced as we apply the gate source voltage. It is not present there beforehand, but only on the application of our gate source voltage, we get a channel between the gate and the source. Now this is what an N-type MOSFET should look like. This is what is called as substrate, or the bulk, or the body. If the bulk is say P-type, we drill two regions of the opposite type of semiconductor material. That is, for P the opposite will be N, and N over here, but it is not only N, it is N positive, which means that it is N-type material, but it is heavily doped. Okay, so this is what is called as source. This terminal is called as drain. Okay, and here we have what is called as the gate terminal, which is a metallic gate here, which is made with the solid line. Okay, and here this portion, it is SiO2. SiO2 is it is a dielectric material. It is silicon dioxide. It is a dielectric or an insulating material which has a very high impedance. So essentially these are the components which are present in a MOSFET. We have the source, we have the drain, we have the bulk, and we have the gate. Okay, so it is a good practice to say that the source and bulk, they are short. What I mean to say is that whatever is the potential at the source, bulk has the same potential. That is, they are connected to a common terminal. Okay, another very important thing with MOSFETs is that it is a symmetrical structure. Symmetrical, what does symmetrical mean? For example, I'll tell you what symmetrical means. For example, we have a BJT. What do we have in BJTs? We have a base, we have we have an emitter, we have a base, and we have a collector. Okay, for an NPN transistor, the base and the collector, they are both N. So does it mean that we can make the N type, which I have, which for example, let me say for example, What I mean to say is that can the emitter and the collector be interchanged, because both are n type? So is it possible that I can interchange the emitter and the collector region? No, I cannot, because collector has different dopings as compared to the emitter, and it has a larger area as compared to